requirements to have topological order. However, you may think about the fact that to obtain a torus in the lab is challenging, is very difficult. So we may think about different sets of boundary conditions that are more realistic and see if still we maintain some of this ground state degeneracy, and in principle whether we are able to encode some information like the logical qubit that I wrote before, also with different boundary conditions. That's why Kitaev and Ravi essentially starting to consider different boundary terms. And in particular, this is the mapping from the toric code on the torus and the generic surface code that is a generalization on generic two-dimensional system. To define a surface code, it is usually important to define these boundary terms. So besides these operators, the Hamiltonian, that involve spins on the bulk of the system, we will define also boundary operators of the vertex kind and of the plaquette kind, which instead are the product of only three spins. Essentially, we have this A on the boundary, which is the product of these three sigma x operators, so it is still able to detect whether we have some sort of excitation, some sort of electric charge in this vertex. And in the same way, we may define a partial plaquette given by the product of three sigma z operators, which is able to detect whether I have a magnetic flux inside this boundary plaquette. So you see that in principle we should distinguish two different sort of edges, a smooth edge and a rough edge, which are characterized by different operators. Apart from that, the important thing is that still these operators A prime and B prime commute with all the other stabilizers. So exactly as before, they must be equal to 1 inside each ground state, and we can specify them simultaneously with all the other bulk operators. And however, since we changed the boundary condition, we do not have anymore the previous constraints that told you that the product of all the A operators was equal to 1 and the product of all the B operators is equal to 1. So in principle we are changing the number of constraints and we are changing the degeneracy of the system. This can be visualized also by considering what are the non-trivial string symmetries which appear in the system. So I define a non-trivial string symmetry, in this case a string symmetry, a symmetry of the Hamiltonian, so it must commute with the Hamiltonian, but at the same time it cannot be decomposed in terms of the terms appearing inside the Hamiltonian, in terms of the stabilizers. And for this particular setup with these boundary conditions, the non-trivial string symmetries which survive are the x along this direction and the z along this direction. This is because here we do not have any constraint on the charge at this point, because we do not have anymore any sort of A here, whereas we know, for example, that there can be fluxes here and there. So still we must host, if we want, an electric charge here without paying any price in energy. So we must, well, we are able to apply a Z string, which essentially moves one electric charge from this point to that point, from the upper edge to the lower edge. And in an analogous way, you may see that we have a horizontal X symmetry, which moves a magnetic flux from the outside here to the outside there, without in the end violating any energy constraint given by the terms in the Hamiltonian. And still, these two symmetries anti-commute. So we have two symmetries not commuting with them, and we are left with a single logical qubit. So we may expect that, we must say that the degeneracy in the ground state of this system, now it is equal to 2 due to these new boundary conditions. As before, you can deform these string symmetries by applying local elements in the stabilizers, but still we are dealing with the ground state, so all the terms of the stabilizers are equal to 1, and this amount just to translating this string in another parallel way, or deforming it in some topologically trivial way. So, in principle, by considering this boundary condition, we store a logical qubit, but most convenient, more convenient scenario is instead to start cutting holes inside our system. So, if I now essentially refuse to measure some of the terms in our refuse to measure, I exclude from the Hamiltonian some of the stabilizers that appear in the Hamiltonian, and I modify these edges through these boundary terms that we have and that involve 3 spins instead of 4. I can define 2 kinds of holes. Of course, they will be extended or smaller, and essentially we have one hole here in which I'm not measuring the presence of the magnetic flux inside here. So I must be careful that there are no electric excitations which violate these terms inside the Hamiltonian, but still I can move a magnetic vortex from the inside to the exterior part of the system. And so we have this first hole which hosts the magnetic flux, and in the same way through the boundary terms given by this plaquette term with 3 sigma z operators, I can define a hole which instead may host an electric charge without paying any energy price. So essentially it is enough to consider that we have 2 different sets of holes, and the important thing is that for each hole I have an additional degree of freedom in my ground state. So for each hole I introduce in the system, I am multiplying by 2 the number of ground states. This is because if I consider one hole, I am defining a new pair of non-trivial string symmetries. The first one corresponds, for example, to a Z symmetry in this case, which moves an electric charge around the hole and detects the presence of an eventual possible magnetic flux inside the hole. And the other non-commuting string symmetry is the one that brings magnetic flux from the outside to the inside of this continuous actually, because it's a dimensional plane with a hole in the middle. So this is true for both the magnetic hole and the electric hole. You just have to exchange the role of the X symmetry and the Z symmetry. Of course, one has to be a little bit careful to the purpose of topological protection in defining these holes, because one of the main points is that if I have periodic boundary condition, I have that the length of the string, the non-trivial string symmetry, scales with the size of the system. Instead, with these holes, you see that we have a string symmetry on the outside, well, this string symmetry Z, which simply scales as the perimeter of this hole. So somehow you may understand that it is less protected than the degree of freedom that we wanted to encode with the full system and the periodic boundary condition. So if we want to try to realize this thing experimentally, we must choose a system size which is large enough in such a way that it is difficult for random fluctuation for a pair of electric charges to be nucleated and move around the hole and be reannihilated. So somehow the perimeter of these holes limit the protection. The bigger I do my rules, and the more protected will be this degree of freedom against, for example, temperature or random fluctuations. The important thing is that, as I said, for each rule I introduce, I multiply by 2 the number of ground states, and so you start to understand why the degeneracy case is exactly as the genus of the system. So in this case, that's the number of holes. There can be some correction due to the external boundary condition, which may be taken in different ways, but still, by increasing the number of holes, you increase exponentially the number of states, of ground states. So, as I mentioned at the beginning, however, there is a problem with the toric code if I use it as a self-correcting memory. And the problem is what happens with temperature. So far we see that the gap that we have in the spectrum protects us against noise or temperature if the temperature is small enough. However, there will be a finite possibility that at a finite temperature I am creating a pair of electric charges, let's say. And so I am moving from the space of the degenerate ground states to the space of the excited states. In this case, of course, I am paying an energy price which is 4. But once I pay this price, these 2 charges will start to move around without paying any additional energy price. So these 2 charges are totally deconfined in the language of Cage lattice theory, or so that you do not have any string tension between them. They are not interacting. They are not linked by some elastic that you may wait to make them free. And so I was saying they are free to propagate, their kinetic energy therefore is 0, and sooner or later, if we do some Brownian motion, I may expect that they go around black holes or go around the fluid system, and they totally spoil the energy that I want, the information that I want to preserve, because this random motion may allow for transition between the ground states. This is somehow the intuitive picture of a phenomenon which is called thermal fragility, which is being studied in great detail, especially by Galileo and other co-workers. To give a more rigorous description of this phenomenon, it is important to understand the partition function of the toric code once I switch on the temperature. So the toric code has the Hamiltonian, which is the sum of A terms and the sum of B terms, and all A and B's commute with themselves. Furthermore, if I consider toric boundary conditions, I have that the product of all the A's and the product of all the B's is equal to 1. However, there is a mapping that essentially tells me that this is the same algebra of 2 different Ising chains taken with 0 magnetic field. Essentially, I can consider A on a certain vertex as mapped in a term which is, let's say, sigma x in vertex, sigma x in this vertex plus 1, belonging to a first periodic chain of the Ising kind, and therefore I have this as 1, the first chain. And the bracket term, instead, I can map it in the same operator, but in a different chain. So I have 2 chains which essentially do not talk to each other completely. And so this is plus 1. You see that all the algebraic relations of these operators are also satisfied by these new operators defined in one-dimensional models instead of two-dimensional models. In particular, you may think that a square must be equal to 1, and this is verified both for your vertex operator and for these operators. The same is true for b square, which is equal to 1. Furthermore, these constraints on these periodic chains are always fulfilled. So the thing is that if you start writing down the partition function as e to beta, the sum of all the possible spin configuration of your Newtonian, this is the same for the two-dimensional toric code, and these pairs of decoupled is in chain without any magnetic field. But for the decoupled is in chain, you know that essentially in one dimension there is no real phase transition. The only phase transition is exactly at t equal 0, but as soon as you switch on some temperature, the fluctuations destroy. And this means in particular that once you consider the average value of an operator sigma x or an operator sigma z, whatever you want, for a finite temperature, so different from 0, in one of these chain, these operators expectation value is going to 0. And Ortiz and Lusinov shows that essentially a single size operator can be mapped in the string symmetry that I wanted to use to encode the quantum information. So what happens is that essentially as soon as I switch on the temperature, we obtain that the average value of the z that I was considering before goes to 0 for each operator z. It means that in a thermal distribution for a Gibbs ensemble, I have not anymore any sort of quantum information stored there. I cannot really recover it. Be careful because this is an information about what happens at thermal equilibrium. However, it does not really say anything about encoding information inside the toric code and then trying to quench the temperature. So it does not give me any information about the time scale in which this expectation value goes to 0 once I switch on the temperature. So that you may hope that there are system sizes that are large enough in such a way that this time scale is long enough for the purpose of storing quantum information. However, this is a first very strong objection on the possibility of really using the toric code as a self-correcting quantum memory. Essentially, it kills the idea of having a self-correcting quantum memory based exactly on the Hamiltonian of the toric code. There are some ways around, some tricks that you may apply to somehow recover some stability of your quantum information. And for the ones of you who know something about disorder, one very nice possibility is to add a small amount of disorder to your system, so in such a way that the coefficients of A now depends on the position, and this small amount of disorder, where alpha of is randomly distributed, essentially allows, localize the excitations. And if the excitations are localized, they cannot move freely away with the Brownian motion, so they cannot really move far enough to disturb my quantum information. Other models instead try to introduce some sort of string tension in between the excitation, and this is another way to reach some confinement. But still, on the experimental side, let us say that this thermal fragility is a very big problem, and it is such that it is not considered any more realistic to really engineer some toric code Hamiltonian in the lab. So either we go to different topologically ordered system, for example, quantum effect system with fractional excitations, or we change our mind, we change our approach, and we consider the toric code as an error correction. This is due to the fact that error correction, in my opinion, is a sort of way of actively implementing the dynamics of the system in an artificial way. So what is error correction? You saw, let us start again from the usual picture of the spectrum that I've already showed you many times. And we want to preserve the information which is stored in a set of degenerate ground states, and we want to avoid any sort of transition from here to there. For the toric code, we know that if some of this transition happens, it means that we are essentially creating pairs of excitations that can be randomly distributed in our system. However, this means that I have a measurement, which is A, to understand if an error occurred. And I can interpret now A and B not anymore as an energy price, but as projectors, as measurements that I do in the lab. So essentially, the trick of error correction is to discretize time. In each time step, I measure a set of all the stabilizers, of all the small stabilizers. So in each time step, I measure all the B and all the A's, and I look whether an error occurred. If an error occurred, I will detect some pair of excitations, either in the A's or in the B's. If no error occurred, well, or if my instruments are not good enough to detect it, I believe that no error occurred, but I do not see any excitation. So once I know that there is a pair of excitation, I can think about artificially applying the correct string operator to annihilate these two excitations, to erase these errors, or for the toric codes it also works fine just to track the position and consider them in post-processing in the end. So the framework of quantum error correction is essentially to define a set of projections that in our case is the set of all the A's and the set of all the B's. And I know that if all of them give me a result plus 1, I know that I am in this subspace of my Hilbert space. Otherwise, if at least one of them gives me different values of -1, I know that I'm not anymore in one of the computational states in which I want to encode the information. So I must be careful either to correct it or to do something else. And this is why these A's and B's are called stabilizers, because by looking at them in the lab, I see whether the information is stable or not. And it is important that all the A's and the B's communicate with itself, because it is telling me that I can really apply this measurement in the lab, and in each time slice I measure all the A's and all the B's. I can do it on the same basis. At the same time, it is important that the stabilizers do not distinguish between different logical states. So if I take that they are all equal 1, I gain no information about the fact that I am in 0, 0, in 0, 1, in 0, and 1, 1 with respect to the non-trivial string symmetries. So this is roughly speaking the idea of using the toric code as an error correction tool. And essentially, in my opinion, we are just saying that we exchange we change our mind and we say, well, A's and B's are not anymore interaction in the Hamiltonian, but they are measurements that we can do, and through these measurements I am imposing somehow an artificial dynamics to the system. Yes, here I say. So, to do this measurement, however, it is important to notice that both A's and B's are the product of 4 operators, essentially an A is equal to sigma x1, sigma x2, sigma x3, and sigma x4. And usually in the lab, it is very difficult to engineer an instrument which is able to simultaneously measure this parity, which is a property of the four spin taken together. And I'm not doing the single measurement, sigma x1, sigma x2, sigma x3, and sigma x4. I just want to know whether this overall parity of the eigenvalues of these single operators is +1 or -1, but I don't want it to specify the full state. So either I have in my lab some instrument that allows me to really do these 4-qubit measurements, and this is a very hard task experimentally. There are proposals in superconductors, or perhaps in the last lecture when we see with majorans that can achieve this, or I invent something else to do this measurement of 4 operators. And the most convenient thing is to add to our system some further spin 1/2, which are these small dots which live on the vertices of the pockets. So each of these spin 1/2, which I will call ancilla, is associated either to a vertex operator, like this one, or to a plaquette operator. And through these ancillas, now we will see that it is possible to perform these measurements by applying only 2-qubit gates, not by considering the product of 4 different spins. To conclude this part of the discussion, I would say that, however, by this structure, I am not modifying the meaning of the physical symmetries. So still, I have that these logical strings, these non-trivial loops that before were string symmetries, commute with all the terms of the stabilizers, so they are not confined by measurements, and if I encode information by exploiting them, this information is not destroyed by the measurement that they imply. So everything that we said about the number of ground states, that now is the number of logical states, and about these string symmetries still also in this picture of quantum error correction. So I was telling you that by the introduction of the ancillas, I am able to essentially read these stabilizers measurement by involving only pairs of qubits at a time and not 4 of them. And in particular, I can translate the A operator and the B operator with these schemes. I don't know if you are familiar with this way of representing qubits. So this strange object is called the control knot. And the control knot is a 2-qubit gate that creates entanglement between 2 qubits and acts in the following way. So you see that there is each line here represents a qubit. So the 4 lines that are labeled psi are the physical qubit of the toric code, and the line on top is the ancilla. The ancilla is initialized in that 0 state. And now we apply, starting from one qubit in the physical qubit set, that in general may represent this state. We apply what is called the control knot, and this control knot is an operator which flips the target qubit, which is the ancilla, if the transport is 0, 1. if and only if the control qubit is in the state 1. So at the beginning, this representation is telling me that I am in state alpha 0, 0 plus beta 1, 0, where this is the physical qubit and this is the ancilla. Physical qubit and ancilla. Once I apply this control knot, I arrive in state which is alpha 0, 0, because when I am 0 in the physical qubit, I do nothing to the ancilla. But here, beta, the second term is transformed in 1, 1, because when this is 1, this operator essentially flips the value of the target. So you may see that the B operator is simple to interpret, because essentially I am on the Z basis and I flip this ancilla each time I meet a 1 in the 4 physical qubits, so that I am really able at the end of the day of measuring the operator B, which was the product of 4 sigma Z. So it's Z1, Z2, Z3, Z4. Simply because I am looking at the number of zeros and ones that I encounter here, and this ancilla starts from 0. If I flip it an even number of times, it will go back to 0. If I flip it an odd number of times, because I have 0, 1, 1, 1, it means that I am detecting an error, which was the previous magnetic flux. The A operator is slightly more complicated because it is measured in a different basis. It's measured in the sigma x basis. So in principle, to solve this problem, I could have considered a schema in which instead of having only a control knot, I decide to change the basis of the physical qubits by adding what is called another AND gate, in such a way that at the beginning this qubit is in the basis plus minus of sigma x operator, whereas inside the other one it becomes it is marked in the same states, but with up and down, so the basis of sigma z, in such a way that I translate this into that, and still I apply the control knot like before, and then I translate it back. And this is a way to measure the number of pluses and minuses. However, this would require another AND gate for each physical qubit, a second AND gate which prepares each physical qubit, and this is not very convenient, but luckily enough there is an inequality that tells me that I can flip the position of the other AND gate by flipping also the position of the control knot. So you see that here you have the control knot as a control the physical qubit, and as a target the ancilla. Here it is the opposite, but there appear these other gates on the ancilla, which is weird. But if you want to do the calculation, you may demonstrate this equality essentially between this setup, which is the one that I am using to actually do the measurement following the definition, and this is equal instead to this other thing where I'm flipping what is the target and what is instead the control. So these two things are equal. And so I showed you the meaning of the first one, while flipping the basis in the physical qubit place, but in real estate it is applied in the other way. Well, these are just details. The important thing is that we reduced a measurement which was a 4-qubit measurement to a set of operations that involve at most 2 qubits. And these operations may be done in physical systems, mainly in the case of superconducting qubits.
It's not completely intuitive, but it is...
No, it is absolutely not completely intuitive. You just have to do the calculation. I never found a way, an intuitive way of explaining this equality. I'm sorry.
But, I mean, intuitively, at least one would expect that the state psi is altered after the measurement. I mean, the state of the physical qubit is altered.
Intuitively it is so, but if you consider the basis of sigma x, then you see that it is not.
Okay.
So, okay. You have to
but then and the state of the ancillary spin is altered instead in this case. How is it altered? Because
it is altered in the way that we want. Essentially, it becomes 1 once it encounters here a odd number of flips in the x basis for psi. Essentially, the non-intuitive thing is that in the control model I told you, well, we have a target and a control. But the information goes in this direction for what concerns the z basis. But the information on the phase, which is on the x basis, goes otherwise. That's probably the cause. So I don't really want to invest a lot of time on this, but it's just to give you an idea that the 4 qubit measurement that I wanted to do may be decomposed in this way using a single qubit and 2 qubit operators. That it is something that in a lab can be achieved with fidelity that are, with accuracies that are high enough.
So you say it can be achieved in the lab, but you have to introduce this extensive number of ancillary qubits to do so.
Yes, so, well, I can go to the one of the last slides, essentially. The status of the art now is to design these systems that are hybrid structures in which these crosses are essentially superconducting islands and are linked between them with microwave guides. And since you are able to control the photons propagating these microwave guides, you may apply to qubit gates involving these superconductors. And so you are telling me, listen, to get something meaningful, you must have a lot of physical qubit of this kind. The state of the art right now is such that there are people, for example, in Delft, who believes that in a few years, let us say 5 years, they may be able to construct structure, let us say, of 13 or 20 physical qubits, that it is not enough to really do quantum error correction and to be competitive with other quantum error correction schemes, but it is enough to provide you a proof of principle that this surface code may work. So the steps that experimentalists in this hybrid structure of superconducting qubits are trying to obtain is first to get a fast enough and accurate enough way of applying all these single qubit and 2 qubit gates, and to design some geometry in which you really must be able to couple a single qubit with 4 other qubits, which is however required for the implementation of the surface code that I'm telling you. Because here, one ancilla, for example, in a plaquette must be coupled to 4 different physical spins, and then this physical spin must be coupled to 4 different ancilla, and so on and so forth. And this is a very nice work of last month by the group of Martinis, with also Pacman that goes around. And essentially these are big systems because I guess that the length scale here is a couple of millimeters, so you can also see it. But the interesting thing is that they achieved very good single qubit measurements, very fast single qubit measurements, because they can do 4 of them at each time in a time scale which is competitive, and to couple all the pairs of these qubits through these cavities, or these big cavities in the middle. don't want to enter really the details, but so there are people that are crazy enough to believe that they can construct these surfaces with let us say 13 or 21 qubits that are the two schemes that allow you for the first efficient, well, effective implementation of this surface code with a sufficient number of single qubits to see something, to encode a logical qubit. And still, to me, it is not really clear whether they want to go on in this way, in which you have really only 2 qubit gates and multiply a lot of them, or if someone is thinking to couple really 4 qubits in some different way, in such a way that you can measure at once really the operators max, 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 max. This is an interesting thing, but still, we were saying that now, what does it mean to create a hole in the system? To create a hole in the system is just not to measure some of the stabilizers in my Hamiltonian. So I can start to measure, for example, this stabilizer, and you see that in this case, here I can either have a magnetic flux or not having it, and I do not detect it anymore as an error, but as some logical state. Of course, as I was telling you before, I must be careful to do this always in a big enough way not to have random fluctuations that spoil the information content of the stabilized states, essentially. But everything that we told before about the statistics and the existence of these string symmetries can be mapped now in an array of Z or X operators or measurements. And in particular, if I at a certain point want to measure the state, the logical state, it is just enough, one of the possible recipes is just to measure this stabilizer, so to switch on it at last to detect whether the state, the logical state is one or another. So, in principle, one hole is enough to encode a qubit, but there are, let us say, software protocols for these quantum error correction systems that instead rely on encoding a logical qubit in a pair of holes. And here you have a pair of magnetic holes, and you see that essentially you may define 2 different string symmetries that are XL, which moves a magnetic vortex from here to here, and so it changes both numbers of magnetic vortices, and ZL, which is instead able to detect the state of this hole. And the trick is to impose at the beginning that there is no magnetic vortex in the system. So, in particular, you may think about the fact that we have the 2 holes, let's say hole 1, hole 2, and in principle here I can have either 0 or 1, either 0 or 1 measuring the magnetic vortices. So the states that are allowed are for 0, 0, 0, 1, 1, 0, or 1, 1. But then, if in this system I use some other string symmetry of the Z kind to be sure that overall there is no magnetic vortex, I remain only with 2 states that are this one and that kind. This one cannot be present anymore. So either I have magnetic vortex here and magnetic vortex there, 2 of them, or I have zero magnetic vortex and zero magnetic vortex. So now you understand why this XL is a Filippo operator for this qubit. It will send 0, 0, 1, 1, vice versa, and ZL instead allowed to measure the qubit by simply measuring the state of a hole. This is very interesting because, as I said to you, we have 2 different kinds of holes. There are the holes with the magnetic vortices and the holes instead that are characterized by electric charges. And still, always in the surface code, you have to consider that these electric charges and magnetic vortices essentially have these peculiar mutual statistics in such a way that if I am able to move this hole around this magnetic flux, then I'm doing something really not trivial, because you may think that I acquire a phase which is -1 only when I have a magnetic vortex here, a magnetic vortex there, and the charge here and the charge there. So for the single qubit, I have that the first logical qubit may be in the state 0, which is, I say, 0 magnetic vortex here, and the state 1 instead of the second logical qubit, state 1 of the first logical qubit is what they call M4. At the same time, for the second qubit, I can define the 0 of the second logical qubit is equal to having 0 electric charges and 0 electric charges, and the 1 is instead equal to having electric charge and electric charge. If I somehow I am able to move these holes one around the other, I acquire an integral phase only when the two states are both equal to 1, because it is the only case in which I am moving an electric charge around a magnetic hole. And this means that if I represent this operation of exchanging one electric hole to one magnetic hole in a matrix, this becomes an operator of this kind, where in this basis I have 0, 0, 0, 1, 1, 0, 1, 1. So I'm creating an entanglement between the two qubits. And this is one of the most important things if you want to do quantum computation. We will go back to similar schemes when we talk about Galileo, because also in that case it is convenient essentially to extend the number of physical degrees freedom of physical qubits which represent a single logical qubit. So you are tracing out the case in which I have a large number of magnetic vortices here. But this was just to say that besides the measurement and the single qubit operations, you are able, there are protocols which allows you to operate 2 qubit gates, for example, the control node. Finally, one has to analyze what is the efficiency of this surface code. So we must ask what are the errors that I cannot detect. So what is the logical error? And if we go back to a picture in which we have a particular boundary condition and I'm encoding the information inside the two ground states of the system with a particular boundary condition, you see that if due to noise two operators X are applied, it means that a vortex is entering in my system. And doing the measurements, I detect the presence of this vortex, and I say, well, this is pretty close to the boundary, so to correct these errors, I have to apply again this sigma x and sigma x and move this vortex back. So that if the string operator applied by the noise is small enough, then I can detect the error and correct it in the proper way. But if the noise is so strong that it applies long string operators, then by detecting the presence of a magnetic vortex here, to correct it, I would say, well, it is closer to this boundary, so I move it back in this direction. But this would result in a logical error, because the noise created this vortex from this boundary, not the boundary which I am correcting. So essentially, you may consider that you have an error that you cannot correct if along one line you have a number of errors that is more than half of the length of the line. And essentially, to evaluate the probability of having an error of this kind along one line, you must consider the fact that for each number of error bigger than the system size, you have the probability of having a single error multiplied to the power L. And this is a combinatorial factor due to the fact that you can take all the combination of L errors inside the big L size, and finally a coefficient due to the number of rows. So this is a very rough approximation of the probability of having a logical error. However, it ends up, well, may be estimated in this way, where I apply the stringing formula. So you see that the probability of having a logical error scales like the probability of having a single error on one link to the power L over 2, which is what we have to consider when we essentially compare this surface code with other error correction protocols. And of course, this calculation is not really realistic, first of all because I have excluded the possibility of having longer strings that wind around. And second of all, because I am considering perfect detection of the errors, so I'm not considering errors on the given syllables. So in the first case, if you account for all the possible geometries of these errors, you obtain that the threshold value for this probability is 15% instead of 25%. This means that if this error decreases above 1/4, of course the probability of error starts to increasing with the system size, which is something that you want to avoid. But if you do instead the calculation properly by considering the parameters of all the ancillaries, by considering all the control nodes which can be noisy, etc., you obtain that the threshold for this error is 0.008. You must therefore be able to apply quantum gates with an error which is smaller than this. This seems small, but actually it is close to what people does in the lab, and actually surface codes are considered the most efficient way of doing quantum error correction, not only because of this threshold which is very high, but because the idea of locality, which was present in the Hamiltonian in the beginning, implies that we have to apply only local qubit operators. So the control nodes that I was showing before are always applied between neighboring qubits. So I already showed you that there are people that are crazy enough to try to build these things in the lab, even though in the next 5 years I doubt that someone will really obtain a surface code. But if you want the data, you see that in this particular setup, they managed to obtain 4 simultaneous single qubit measurements, which is difficult usually to apply them all the time, with an error which is around 1%, so not so distant from that 0.008, in a time which is 200 nanoseconds, and that you have to compare with the coherence time of the system, which is instead of 10 nanoseconds. So you see that you may apply this operation many times inside the coherence time. And this suggests that this superconducting structure sooner or later may allow to build quantum memories that are stable enough. Here I had other examples of the fidelities that one can obtain. Of course, the fidelity decreases once I try to apply quantum nodes or 2 qubit gates, and this is a problem, but still, well, there are lots of interesting developments, and I guess that I can end here the lecture. So that's what I wanted to say. I leave you with a list of references. In particular, I suggest you to read, if you are interested in these things, this didactic reference by Calabrese and Naumann that you find on the archive, and it was taken from the lectures that Kitaev gave in this issue in 2008. In particular, in this reference you will find the introduction for the toric code, seen as from the Hamiltonian point of view, and it will be useful because inside this review we will find also information about the minor chain that we will face in the third lecture, and also other more advanced things that I'm not going to tell you in the next lectures. Otherwise, if you are interested, you can look to the original papers that usually have a part which is very understandable, and instead there is a part of generalization starting from the historic code by implementing different groups and different things, which becomes much harder to follow, and it requires a very strong mathematical background. Instead, if you are interested about the toric code as a surface code, so the quantum error correction scheme, there is a recent review by Fuller which contains everything you could imagine about surface codes. It's very extensive and detailed. Otherwise, there is a more introductive reference by Vincenzo, which speaks about the possibility of implementing surface codes in structure. With that.
Just questions? Everybody's starving to. But anyway, if you have questions,
yes,
Michele will be here for the next day. Yes.